one algorithm which was a real breakthrough in the area of neural network and made neural network become famous was backpropagation. And actually, backpropagation was a way to compute the derivative of the cost function with respect to one of the parameters, which is the weight, right? So in the case of perceptron, it was easy, it was trivial to compute the error with respect to weight, W1, WD. That was my weight. It was easy to compute the derivative of error function with respect to this beta. Now I have many of these perceptrons in different layers. I have many of these layers. And the cost function here, this is my output y hat. And there's a true y. And with some cost function, I want to minimize the distance between what I predict and what it's supposed to be. But I need to take derivative of this cost function with respect to this weight, for example, with respect to this weight. But it's a very complicated function, As I told you, it's f of f of f of f of. It's many nonlinear function has been applied to get to this point, and it's not trivial to compute the derivative. And backpropagation was a way to compute the derivative. Okay? And now we want to learn about backpropagation. This is just a snapshot of a neural network. So I have, say, for example, layer L, layer I, and layer J. In each of these layers, there are many perceptrons. Okay? And somewhere here, I have the output, and somewhere here, I have the input. So I have many layers. I have chosen only 3 layers and 3 perceptrons of these 3 layers. In each layer, 1 perceptron. So I told you that each perceptron has 2 parts. The first part is just a linear sum of the input. And the second part is a nonlinear function applied to this weighted sum, right? So this part A, is just a linear sum of the input. So A is sigma of ZIUIL. This is UIL. This is one of the weights of the input. This weights times whatever was the output of the previous layer. When I take the summation of this over all inputs, that would be the value of AI. Okay? Then in the second part, I apply a nonlinear function to this AI. In the traditional and conventional way of doing perceptron, this nonlinear function was a step function. Step function is not differentiable, and that was one of the reasons that we had a hard time, to change our cost function, the summation of distance. Yes?
Now they use values, and those, by the same time, those aren't differentiable.
Yeah.
Right?
Yes. Yeah.
So differentiability doesn't, like in this case, it's on each interval.
In each interval, yeah, you're right. But I will mention this in a minute, that what's the role of this. So this nonlinear function which we apply to A could be any nonlinear function. And there are some popular nonlinear function. One of them has this form, a logistic function. Another one has exactly the same form, but the difference is that this is between -1 and +1. You could have the same form between 0 and 1. So logistic function or tangent hyperbolic function. And recently there is a function which is called ReLU, rectified linear unit, which has this function, which I get to this in a minute. For the moment, forget about this one. So there's a nonlinear function applied to A. And this nonlinear function, for example, could be a logistic function. It could be other functions. Okay? So this is in terms of notation. And this network, has some layers. At the end, it produces, yes?
So a question about the notation.
Mm-hmm.
So what is the UI I?
This is UIL. And this is ZL. This is ZL times UIL becomes AI.
And that is summed over all.
Sum over all of these ZLs. You have many perceptrons on the layer L. Each of them have an output. I call the output of perceptrons of this layer ZL. Over all of them, multiply by the corresponding weight, sum, it will be AI. Right? Okay, so there are many layers here. It's somewhere here I predict y hat. Okay, and then I want this y hat to be close to y. Let's go for the simplest cost function. And my cost function is y minus y hat squared. Okay, so I want y to be close to y hat. But my job is to take derivative of this cost function with respect to one of these weights, one of these parameters. Derivative of y minus y hat with respect to UIL. Any suggestion how we can take this derivative? Yes. But in fact, backpropagation is basically chain rule. You apply chain rule multiple times, and the chain rule and recursion. Okay. So it's not quite clear how can I take this derivative with respect to UIL, but I can apply chain rule and write it as derivative of y minus y hat with respect to AI. And then derivative of AI with respect to UIL. Okay. Now, how does this chain rule help? So what is derivative of AI with respect to UIL? AI with respect to UIL. Sorry?
Again, we can split it.
You remember, we have layer L. We have layer L, we have layer I, and we have layer J. And AI is simply summation of all of these z's times corresponding weight. So basically AI is this z times corresponding weight plus this z times corresponding weight plus this z times corresponding weight. And now I'm taking derivative of AI with respect to one of these weights. So what would be the derivative? The corresponding z, right? So derivative of AI with respect to UIL simply would be ZL, the corresponding z, right? So I know this derivative. But what's the derivative of this cost function with respect to AI? This is hard, actually. I don't know what that is. So I call this the hard part delta I. I don't know what the delta I is. But this part I know. It's ZL. So the derivative of cost function with respect to UIL would be delta I, which I don't know what delta I is, times ZL, which I know. Now I have problem with this delta I, so I have to compute this delta I somehow. So delta I is derivative of y, derivative of the cost function with respect to AI, which was hard to compute. Okay. Now, any suggestion now how to approach this? Yes.
Use chain rule again.
Use chain rule again for
On Zi.
on Zi. Okay. So I have derivative of y minus y hat with respect to AI. So you suggest that I write it as
Derivative with respect to UGI.
derivative with respect to
Respect to Zi.
Zi.
And then di Zi by di AI.
Okay. So how does this help?
You can
Sorry?
you can continue in that manner until you get to your output layer.
No, if I do I know that what's the derivative of this with respect to Zi? No, I mean, I have another quantity which is unknown. And do I know the derivative of Zi with respect to AI? This I know. I mean, this is easy, but this I don't know. So I had a quantity which I called it delta I, which is unknown. But you can compute this unknown quantity based on another unknown quantity. And then I have to do something about this one. Right? But I have a better suggestion, actually. Actually, I don't have the better suggestion. Those who invented backpropagation had a better suggestion. So I want to take derivative with respect to AI. Why don't I take derivative with respect to AJ and then AJ with respect to AI? Why this is a better suggestion than your suggestion? Because derivative of this with respect to AJ is just delta J. It has the same nature as delta I, which was unknown. If I can handle this, it means that to take derivative of the cost function with AI of one layer, I can express it in terms of delta of another layer. In your suggestion, it was altogether a new quantity, which has nothing to do with, but it has the same quantity just for another layer. Okay? So is this chain rule correct? There's something missing here. Sorry? Summation. Summation over here? Summation over all j's. Why should I have this summation?
Because AIs depend on all the AJ before.
Exactly. You know, what's the meaning of this derivative? It means that I perturb I, and I would like to know what's the effect of perturbing AI on this cost function, right? And the chain rule tell me, okay, you want to know what's the effect of perturbing AI on this. I will tell you that it's can be written as if you perturb AJ and then you, to see how AJ changed the cost function, and then you perturb AI and see how AI changed AJ. But so I have to perturb AJ to see what the effect of AJ is on AI, but there's many of them, you know. Any of these AJ, if I change, if I perturb, they're going to change this, right? So it's a summation over all of them, not only one. So so this is AI, and AI can be written as summation over J of this cost function over AJ, and then AJ with respect to AI. And this part is just simply delta J. So I was about to compute delta I. Now I can express delta I in terms of delta J. Okay. So this is delta J. But AJ with respect to AI, how can I approach this part, the second?
And we can use that derivative.
Yes. You know, I need derivative of AJ with respect to AI. I can write a chain rule again for this part. AJ with respect to ZI and then ZI with respect to AI. Then I can compute both of them. You know, so I write AJ with respect to AI, AJ with respect to ZI, and then ZI with respect to AI. AJ with respect to ZI is what?
UJI.
Simply UJI. And what is ZI with respect to AI?
Function.
Sorry?
Derivative of that function.
To compute the derivative of that nonlinear function, sigma, right? Sigma was a nonlinear function applied to AI and produced Z. So derivative of Z with respect to AI would be simply the derivative of that function, whatever that function is. Okay? So this is UJI. AJ with respect to ZI is UJI. And ZI with respect to AI is just the derivative of whatever nonlinear function I have chosen at point AI. So what's good about this is that I can express delta I in terms of delta J. So remember what we did at the beginning. You know, we wanted to compute the cost function with respect to UIL. And we realized that this is going to be delta I times ZL. ZL is known. Delta I is unknown. But delta I itself can be computed in terms of delta J. Delta J itself can be computed in terms of delta K, right? And I can go over and over and over up to get to the last layer. And I can show you that delta for the last layer is trivial to compute. Then you can come back, right? You can come back. It's a recursive function. You know, you need the derivative of this one. It depends on this one. This one depends on the next one. Get to the last layer. And last layer is trivial to compute. Then get back. Okay, then you can compute all of them. So, you know, this sigma, for example, is a sigmoid function. Then the derivative have this form, usually has a closed form. And, you know, that was the formula that we had here. And note that this can be out, you can take this out of the summation because it has no index of J. You know, delta I is basically sigma prime AI, then sigma this quantity. And that's what we have here. You know, we can take this out of this summation. So, and this is the recursive definition of delta I. Yes?
Do you assume that sigma is differentiable from this?
Sorry?
Do you always assume that sigma is differentiable?
Yes. In ReLU that I mentioned, it's not differentiable, but I will get to that in a minute. But yeah, you assume that it's differentiable. Okay. Now, you know, suppose that you have all of these layers and you want to compute the delta for the next layer, the next layer, and the next layer. And suppose that the last layer is this one, K. At layer K, which is the last layer, what's going to happen? You know, a perceptron has this part A and Z, and delta is derivative of y minus y hat with respect to A. That's the definition of delta. Now I'm going to compute delta for the last layer. In the last layer, the output is y. You know, without loss of any generality, I'm going to assume that the last layer doesn't have Z. It's just A. Why I say without losing any generality? Because, you know, if this is your function, if this is your network, and your last layer has Z, I'm just going to add a new layer to this, which doesn't have Z. And whatever this Z is goes here and goes out. Doesn't do anything to it. So just for simplicity, assume that the last layer doesn't have Z. And then I have to take derivative of my cost function with respect to A. But what is A? A is really y, right? Because there is no nonlinearity. You know, something happened here, which I don't care, and you have A. I don't apply any nonlinear function to A, just the output would be whatever I computed, A. I call it y hat. So y hat is A. So in the last layer, when I take derivative of the cost function with respect to A, in fact, I'm taking derivative of cost function with respect to y hat, which is trivial to compute, right? It's just 2 minus 2 y minus y hat. That's my derivative at the last layer. So basically, at last layer, it's trivial to compute. And then you can compute, you know, the previous layer, because previous layer, the layer just before the last layer depends on the last layer. So you can compute that. And then you can compute the layer before, and you can compute the layer before. So you can compute all of them to the first layer, right? So I can compute the derivative for all layers now. So you can see that, in fact, there's 2 steps. You know, the network, actually, the information in the network go forward to compute y. But to compute the derivative, you go backward. You backpropagate this derivative until you get the derivative of the first layer or any layer, right? There are 2 passes. The derivative will be backpropagated. And the information is going to go forward to the network. Okay? And this is the base of backpropagation algorithm. So in backpropagation algorithm, you have a network, and you feed the network with 1 data point. But, okay, how this network is going to compute the output for this data point? You're going to assign some weights to the network just randomly. Choose some random weights. That's your initial value. And it's good to choose this arbitrary random weights close to 0. And we'll see the reason later on. So choose some weights close to 0 as random weights, arbitrary weights for the network. So you have some weights, feed the network with 1 data point, and then compute the output of each perceptron and the next layer and the next layer and the output. So you have some y hat in the output. So when you apply X to the network to input layer, calculate the outputs of input neurons. And then you propagate the output of each layer to the next layer until you get the output. When X reaches the output layer, so you have y hat, then you can compute basically this quantity for the last layer. You know, for random weights, you have y hat. Now you can compute this quantity for the last layer. Now you can backpropagate this delta to compute the delta of the previous one, previous one, previous one, and compute the basically using this recursive formula. You can go back, and then you have delta of all layers. Delta of all layers, you have delta I, you have delta j, you have all of the deltas. Then when you have all of the deltas, it's easy to compute the derivative, because derivative was simply delta I times ZL, and you have the ZL. ZL is the output of a perceptron. And you have the delta, and you compute, you have the derivative with respect to that weight. If you have derivative, then you can apply gradient descent to that weight, the same way that we apply gradient descent to perceptron. So the new weight will be the old weight times some learning rate times the derivative with respect to UIL, which this derivative doesn't have a closed form anymore, can be computed using this back and forth algorithm, which is called backpropagation. Okay, so the search algorithm still is gradient descent, but the way that we compute the gradient is backpropagation. Okay. So that was for one data point. For this data point, I'm going to update my weights. So I started with some random weight. I feed the network with 1 point. So I will update my weights using this data point. Now feed the network with the second data point and do the same thing. And with the third point and do the same thing. And with the last point n and do the same thing. When you do one pass of all of these points, it's called one epoch. Okay? And usually you have to go through many rounds until it converges. And in practice, actually, when you go through many rounds, in each round you basically shuffle the points, You don't keep the order, from 1 to n. In the next round, you shuffle the points to avoid local minima, to avoid oscillating between some weights.